Welcome to Yaka Digital Network videos. Look closely at this spool of copper wire. It is a cornerstone of global industry, largely because it can be hammered, pulled, and bent continuously without snapping. Contrast that with these heavy salt rocks. If you apply the same mechanical pressure to them, they do not bend. They shatter instantly. Both of these materials are solid structures, held together by intense electrostatic forces. Yet their physical responses to mechanical stress are complete opposites. In advanced level chemistry, we do not memorize physical properties like malleability or brittleness. We deduce them directly from atomic structure and chemical bonding. To understand why a metal bends and a salt shatters, we must look past the surface and examine the microscopic bedrock where these bonds operate. We will deconstruct ionic, metallic, and covalent bonding, apply VS-EPR theory to map out precise three-dimensional shapes, and analyze how intermolecular forces define the exact states of matter we observe. Ionic bonding occurs when electrons are completely transferred from a metal atom to a nonmetal atom. In this diagram of sodium chloride, the sodium atom loses one electron, transferring it to chlorine. This creates a positively charged sodium ion and a negatively charged chloride ion. According to Coulomb's law, the strength of the electrostatic attraction between these ions increases dramatically with higher ionic charges and smaller atomic radii. This attraction is non-directional. Instead of forming isolated molecules, the ions build a massive, repeating, three-dimensional cubic arrangement known as a giant ionic lattice. This exact geometry explains the material's physical limitations. Watch what happens when mechanical force is applied to this perfectly aligned structure. The force shifts the plane. Suddenly, positively charged ions are forced directly next to other positive ions, and negative next to negative. This alignment generates violent electrostatic repulsion, cracking the entire crystal in half. This lattice structure also dictates electrical conductivity. Because the ions are locked in fixed positions, solid salt cannot conduct electricity. It only becomes conductive when molten or dissolved in water, which allows the charged particles to move freely. Ionic solids are brittle because any physical force that shifts their internal lattice forces identical charges together. The resulting repulsion shatters the material from the inside out. If shifting a lattice destroys an ionic solid, why can we hammer or stretch metals like copper into thin wires? This diagram illustrates the metallic bond. It consists of a rigid lattice of positive metal ions, fully submerged in a flowing sea of delocalized valent electrons. Because these electrons are not bound to any single atom, the positive ions can slide smoothly past one another. The electron sea stretches and adapts, maintaining a constant electrostatic attraction that prevents the structure from breaking. However, pure metals are often too soft for heavy industry. To solve this, metallurgists create alloys by introducing elements of different sizes, like adding carbon to iron to create steel. Looking at this split screen, the pure metal on the left slides easily, but in the alloy on the right, the mixed-size atoms physically disrupt the regular layers, blocking the sliding planes and locking the structure in place. Metals bend because their delocalized electron sea acts as a flexible electrostatic glue. Alloys are stronger because different-sized atoms disrupt that regularity and prevent the metallic layers from sliding. Unlike metallic or ionic bonds, covalent bonding involves the directional sharing of electron pairs between specific atoms. This sharing forms distinct finite molecules rather than infinite lattices. A specific variation is the dative or coordinate covalent bond. In this case, both shared electrons originate from a single atom's lone pair. Here we see an ammonia molecule and an electron-deficient hydrogen ion. The nitrogen atom uses its lone pair of electrons to reach out and capture the hydrogen, forming a positively charged ammonium ion. Despite originating from a single atom, once a dative bond forms, it behaves exactly like any other standard covalent bond. Both covalent and dative bonding lock shared electrons into specific directional pathways. These pathways ultimately determine the exact three-dimensional geometry of the resulting molecule. To predict those specific shapes, we use valence shell electron pair repulsion theory, or VESPR. The core principle is simple. Regions of negative electron density physically repel each other, arranging themselves as far apart as possible to minimize that repulsion. This creates a strict hierarchy. A lone pair of electrons repels more strongly than a bonding pair. So lone pair repulsion is the strongest, followed by lone pair-bond pair, with bond pair being the weakest. This 3D model of methane shows the baseline geometry for 4 bonding pairs. The bonds space themselves out symmetrically into a tetrahedral shape, locking the bond angles at precisely 109.5 degrees. Now look at ammonia. It also has 4 electron regions, but one is a bulky lone pair. As it pushes down on the 3 bonding pairs, it compresses the geometry into a trigonal pyramidal shape, shrinking the bond angle to approximately 107 degrees. If we shift to water, we introduce a second lone pair. These 2 invisible, bulky regions squeeze the remaining oxygen-hydrogen bonds even closer together, forcing a bent shape and compressing the angle further to 104.5 degrees. The physical 3-dimensional shape of any covalent molecule is dictated entirely by this invisible war for space between competing electron regions. Geometry directly controls polarity. A molecule can contain polar bonds, where one atom pulls electrons harder than the other, but still be completely nonpolar overall if its shape is symmetrical. Consider this linear molecule of carbon dioxide. The oxygen atoms pull electron density away from the carbon, creating polar bonds. But because the dipole arrows point in perfectly opposite directions, they cancel each other out entirely. Now look at water. Because of its bent VSEPR geometry, the individual bond dipoles do not cancel. Instead, they add together, generating a massive net molecular dipole. Water is highly polar. This molecular polarity determines the intermolecular forces, or IMFs, that act between separate molecules. These range from weak London dispersion forces to stronger dipole-dipole interactions, and finally to hydrogen bonding. Hydrogen bonding requires a hydrogen atom attached directly to nitrogen, oxygen, or fluorine, interacting with a lone pair on a neighboring molecule. In this network, the strong electrostatic pull between the oxygen of one water molecule and the hydrogen of another forms exactly that bond. When you multiply those hydrogen bonds by the trillions, you get the macroscopic properties of a river. It takes a massive amount of thermal energy to break these specific intermolecular forces. That is why water is a liquid at room temperature and has an exceptionally high boiling point. The microscopic forces dictate the physical state of the environment we navigate every day. The macroscopic world is entirely governed by microscopic rules of attraction and repulsion. Whether you are observing the extreme melting point of a diamond, the malleability of copper, the brittleness of salt, or the boiling point of water, the properties you see are a direct result of chemical bonding and molecular geometry. Now it is time to apply these principles to unfamiliar compounds. Competency challenge. Predict the shape, approximate bond angle, and polarity of PCl5 and SF6. You can watch more videos for all classes here and get all content at www.yaka.cc.